Hi, everyone. My name is Chad, and thanks for joining us. And today we're going to talk about reinventing geospatial analytics. And I'm joined today by Joe Bettridge from TELUS. And the key point of this talk is going to be to describe what becomes available to users and customers and their users when you really take the brakes off geospatial analytics.
Hi there, I'm Joe Bettridge. I lead the TELUS Insights consulting program at TELUS. We are a heavy user of Google BigQuery as well as BigQuery GIS.
Right on. And Joe and I are both excited to show you what we've been up to. So yeah, here are the two of us. We're your speakers. I'm a product manager at BigQuery, and I'm also the GIS lead for Google Cloud.
And I am the consulting practice lead for TELUS Insights.
Right on. Okay, so without further ado, let's go ahead and get into it. Um, we'll talk about use cases, and Joe is going to go through some of like the algorithms that TELUS is using inside of BigQuery GIS. But to set that up, I'm going to go through a couple, call it terms of art. We're going to go through BigQuery just a little bit and what BigQuery GIS is. And then we're going to get into some more details. So if you're already very familiar with the product, just put me on 1.5 times speed for the next minute and a half. So with that, let's jump in. For those not familiar, BigQuery is Google Cloud's enterprise data warehouse. So looking at the left side of the screen here, we're primarily an analytics tool. And the product's real claim to fame here is that we can scale from gigabytes to petabytes without encumbering the user with having to manage any of that infrastructure. You interact with the product in SQL, so it essentially looks like a relational database that can scale up to petabytes. Data inside of BigQuery is encrypted, durable, and the product is highly available. As a matter of fact, we just launched 4 nines of availability as our new SLA, which is industry leading, which is really cool. We want to make the product as differentiated and useful to users as possible. So we have a couple unique items that I wanted to talk about. The fact that BigQuery is fully managed and serverless those are the things that enable us to scale to petabytes without making users provision hardware and things of that nature. We have a real-time streaming API, so you can stream data straight into BigQuery. And then using the BI engine, which is on the bottom of the list here, you can actually query that in real time. So you can do real-time insights on data streamed right into your data warehouse without having to use any other tools. We've also invented some new SQL verbs so that you can do machine learning right inside the platform. And what this talk is all about is some other SQL verbs. We didn't invent them. We're using the PostGIS syntax, but by bringing geospatial SQL functions and geospatial data types into BigQuery, we're enabling a whole new class of use cases inside the product. So let's dive in. What is BigQuery GIS? First and foremost, it's supporting a new geography data type. We launched this to alpha a couple years ago in 2018. It's since gone GA. So this is a very solid offering inside the product. And a geography data type, as you can see, can have several different shapes. Points, line strings, polygons, multis, collections, all of these fit inside the geography data type. To operate on those data types, we have a number of different functions. So we've got about 50 or so PostGIS syntax functions that we've implemented inside of BigQuery. And these function types take the categories here. And they cover all the primary and the majority of the functionality that folks use inside of PostGIS. What's really exciting about some of these, though, is that particularly the predicates, you can do geospatial joins based on predicates. So if you want to join two tables based on whether a point is inside a polygon, that is totally within bounds. If you want to do that on data sets that are really big, like terabytes or hundreds of terabytes, that also is totally within bounds. And Joe is going to talk a little bit more about what becomes possible when those limits are relaxed for your workloads. Speaking of workloads, almost any analytics workload, whether it's geospatial or not, has these components. First thing, you need to get data into your product or into the data warehouse. So that's the ingest here. Then you have to analyze it inside the data warehouse. And then, results as a table are interesting for some result sets, I suppose, but really you want to visualize that. And particularly for geospatial, you want to visualize those on a map. And so I wanted to call these out because there are some aspects here that BigQuery and BigQuery GIS are really strong at, and there are some places where we need our partner tools to really flesh out these workflows. So I'm going to go through from left to right. So in ingest, BigQuery has a load API and a streaming API. And so if you want to, a lot of our, for example, industrial IoT customers are using the streaming API to stream instrument or sensor data straight into BigQuery tables. We have customers using the BigQuery Load API to load as much as a petabyte per day. And we have customers using the streaming API to load up to 10 gigabytes per second per table. So that handles data that's, that we would just want to flow straight in. But let's say you have data sets that are in specific geospatial formats. For that, we've partnered with Safe Software, and they have written a BigQuery emitter for their tool, FME. So this tool allows you to import and materialize as a BigQuery table any number of the hundreds of geospatial formats that they support. So if you've got shape files or KML or GeoJSON or what have you, geospatial data format X, chances are FME supports it, and you can bring that straight in using a drag and drop tool into BigQuery. So ingest, cool stuff. Now, the real strength of BigQuery shows up in this analyze column. In that BigQuery, as I mentioned before, the strength of this product is that it can process data at the petabyte scale. And so when you add geospatial analysis to this, you can now process GIS data at the petabyte scale, which really hasn't been possible before. And so this type of data, I'm really talking about structured and semi-structured data. For imagery data, we have to turn to tools like Google Earth Engine and Descartes Labs, and I'll talk about those in a little bit more detail later. So once you've done your analysis, let's move on to serve and visualize. Specific or particularly with geospatial analyses, you don't look at a table, right? You want to see your results on a map. And we have a multitude of tools, some of them specified for different personas or different types of users, to put those results in a map and then serve them either as a report or as a portal or just as an image for that analyst. The ones I've highlighted here in bold are ones that have direct connectors to BigQuery, so you don't have to extract a file and then transform a file and then render it. So there's a healthy selection of folks that connect directly to BigQuery. So let's talk about a couple of these tools in detail. First off, let's talk about Google Earth Engine as it performs on imagery analytics. So Earth Engine is a tool, a product at Google. It's been around for about 10 years, and it has an immense data catalog of satellite imagery. It's about 30 petabytes. And the thing that's really cool about their data catalog is that when new satellite imagery comes in, Earth Engine as a service will automatically register and orthorectify that imagery so that it is includable in your analysis with a single line of code. So for example, like pound include, for those that speak C, right? Pound include sentinel imagery from this date, date A. And boom, that's it. And now you've got the entire globe of sentinel imagery from that date. You can then include sentinel imagery from date B to do an A-B comparison, again, with just a couple lines of code. Very cool stuff. Descartes Labs is another image processing tool that connects directly to BigQuery. They themselves have an immense data catalog, and some of these thumbnails here describe elements of it. For example, like SAR imagery, AIS, which is automatic actually, I've forgotten the acronym to that, but that one's actually ship positions, showing shipping lanes all over the world. They also have a dedicated solutions team. So if there's an aspect of this data that you want to process and you need some support, Descartes Labs has a lot of detailed expertise to help you along. So The next few slides, we're going to step in and kind of go persona by persona. So analysts, if you're an analyst, you speak SQL, you're using BigQuery, you look in the documentation, you figure out which ST commands you need, and you write your query. And you just want to see those results on a map to understand understand what your results are. BigQuery GeoViz is an excellent tool for that. So you can either write the query in the UI, and then there's a drop down where you can explore it directly in GeoViz. You can compose your query in the GeoViz window, which then runs it against BigQuery. And then that allows you then to do interactive styling and visualization, pan and zoom. This is all on top of Google Maps. We've also done a bunch of upgrades to this little product over the last few months. So we've blown away the visualization limitations. And so it's essentially you can render as many points as your browser can hold. And we've enabled the ability to share maps with colleagues. So this is not a full-featured geospatial analysis platform. Like I said, it's a way to get your query on a screen so you can understand it. But it's a handy little tool that we like quite a lot. So for developers, BigQuery GIS is also supported by the Google Maps API. So you can bring BigQuery data straight into your map applications and map visualizations. So you can see here, this is actually a heat map of taxi trips in Manhattan. So that center image is the island of Manhattan. And then the API has some really nifty ways to call out specific areas, which are shown in the two images on the right. Now, business users, if you're not an analyst and you're not a developer and you just want to operate in a BI tool, again, we've got you covered here. Both Data Studio and Looker have support for BigQuery GIS types or BigQuery geography types. And so you can use these tools to create dashboards on top of pan and zoomable maps. Now, one element that we haven't touched on yet that I'm very excited to announce today, right now in this section, is the Carto Tiler. With BigQuery, you have the ability to process enormous volumes of data. The tools that I've shown you before are very, very capable, but they don't have the ability to render the same level and same magnitude of volumes of data that BigQuery can. And Carto, our partner, has solved that. And what they've done with the Carto Tiler is they've created a way to create a hierarchy of data corresponding to zoom levels here. So what you're seeing in the right image is the building locations pulled from the OpenStreetMap dataset, which incidentally is available in BigQuery public data. So you can create this map as well. And there are 300 million dots worldwide on this map. And so if we click into that map, you can see how fluid and detailed the rendering is as you go from street level all the way back out to orbit. And as again, we're announcing this the availability of Carto's beta today. There's some links over here on the left-hand side, so you can play with this map yourself. And there's an email address there for you to send a note to get more information. So just in case you thought the Carto Tiler only worked on points, here's an example on polygons. So we're going to zoom in here again on New York, where the southwest corner has some really interesting shaped apartment buildings. So the links here are on the slide on the bottom left, and we are very excited to announce this with our partner, Carto, as now visualization can approach the same scale as BigQuery's native compute. So very exciting stuff. Thank you. All right. The last section before I hand it off to Joe is I wanted to talk at a high level about the use cases that we are seeing our customers employ BigQuery GIS. So starting on the left-hand side, in retail, the primary operations in retail that we've seen are channel optimization, site selection, and marketing analysis by trade area. Because BigQuery allows you to define your own polygons, obviously, like you can define your own data-driven trade areas rather than using the established ones like either census blocks or zip codes or any other kind of established polygon. You can define your own that are specific to your business's needs, and then run whatever aggregations you need, again, because the scale will support you. In supply chain and logistics, we've seen a number of our customers use IoT, so Internet of Things data, to do traffic analysis, which is what this image shows. This is actually a heat map of ML predicted hazardous driving areas developed by our partner and customer Geotab. So they actually used vehicular data combined with weather data that's already stored in BigQuery to do a GIS plus machine learning tool to say, you can dial in a weather condition and then have that predict what the hazardous driving would be for that weather condition. So very useful for city planners and traffic planners. We see a lot of activity around delivery optimization, and really gratifyingly, we're seeing some significant projects around supply chain sustainability. So this is calculating the human cost, the economic cost, and the environmental cost of taking product from its source, which may be many, many thousands of miles away from its ultimate destination on the shelf before you buy it. And so knowing the true cost of that supply chain and being able to optimize that supply chain to make it economically, environmentally sustainable is really exciting work. We all know how important public dissemination of data is in this time and age. And so we've seen a number of US states and countries around the world use BigQuery GIS and our dashboarding tools to support public data portals. Also, very interestingly, this is an air quality map from our colleagues at Aclima and Geotab, where they're actually discovering, one, that air quality can change on a block by block basis, and two, that the reduction in human travel during these COVID times has greatly reduced the pollutants in the air. And they have a lot of research that they've used BigQuery and BigQuery GIS to support. And then lastly, in agriculture, we've seen a lot of usage around a yield optimization, so trying to get the most food production out of a field that you possibly can. And then once you've figured it out for the field, because these tools, BigQuery and in this case Earth Engine, operate at such scale, you can do these analyses for the entire globe in one shot. And so that way, S4 AgTech, another one of our customers, is doing worldwide production forecasting, where like figuring out how much grain the Ukraine is going to do is just one step of their process, because they can do that for the Ukraine, for Argentina, the entire globe in one shot. So with that, let me wrap up my section. I've given you a very high level introduction to both BigQuery, BigQuery GIS, and some of the partner ecosystem and use cases. And I'd like to hand it over to Joe now to tell you what TELUS is doing in detail.
Perfect. Thank you for that, Chad. So just to get us started, for those of you who are not from Canada and don't know who TELUS is one of the largest telecommunication companies within Canada. So we represent about 9.5 million of the 35 million Canadians on their cellular plans. And one of the things we've been doing for the last while is we've been developing an insights product that allows us to use massive amounts of de-identified aggregate data to answer really complex questions about the real world. And what we want to announce today is that we're creating an API into this data that is launching today that allows for users to query this data directly and get aggregate results back that have no individual information in them, but can answer really complex business problems. This is a first for us, and it's one of the first times in the world that an API into this type of data has been able to be generated, and that's thanks to BigQuery GIS. So the big picture of what we're trying to do is we're trying to solve the problem that many businesses have today of making critical decisions based on gut feel, small sample rate surveys, and strawman business cases. We've had this promise of big data for a very long time, yet we haven't seen a lot of delivery on it. We've just seen mass amounts of data be stored, but no real analysis has been capable to be completed that can really solve the questions that businesses and governments have. Usually this is for one of two reasons. Either the technology is a roadblock or privacy has been a roadblock. And as I'll talk about in the next few slides, both of these things have been solved using both BigQuery and the previous groundwork we've laid around privacy. And we need this to be scalable. This is a really critical issue. Government's existing BI tools need to be integrated and it needs to be able to be used within the current supply chain of data. We can't be trying to create a new set of tools. We need integrations directly to the tools today. As Chad was talking to earlier, the BigQuery GIS is really great for plugging into a lot of different tools that we commonly use. So what is TELUS Insights? TELUS Insights takes all the aggregate information being generated by our cellular network. So every time a phone connects to a cell tower, there's a residual event that's created that says this phone was at this cell tower at this time. We take all that information across the country, we remove all the identifiers, we get rid of anything that's personal from that, and we create a row level record saying this is the data of what happened across Canada. We then upload that data into the cloud, process it, remove a lot of the secondary information that's not necessary, and then we start analyzing it and producing insights. These insights could be that there were 10,000 people in a neighborhood at a time that spent at least 2 days there in the last week. It could be the trade area of a given business, maps around a certain area. The primary area of trade is within 5 kilometers of the business. The secondary area is within 7 kilometers to the east and only 3 kilometers to the west. We're able to pull this all out and aggregate that through. And finally, we're doing these results through an API that's powered by Google Cloud. And all of this, we need privacy. Privacy is a critical cornerstone of everything we do around insights. TELUS has worked very closely with Anne Kavukian, who's the former Privacy Commissioner of Ontario, on achieving Privacy by Design certification. This certification entails ensuring that all privacy and regulatory issues are met. The language she wrote has influenced the GDPR and has been seen there throughout. What we do specifically is we add in privacy controls, including de-identification. So before we analyze any data, we're de-identifying it. We aggregate all of our information into large data pools, so we don't allow anything about individuals or even small groups of individuals. Further to this, we extrapolate all the data to match to our market share, so it represents the entirety of the country as opposed to only TELUS's share. We also include security within this, so we do a lot of work on security and making sure this product is secure by design. All engagements beyond this are also audited by our trust model. TELUS views trust as a cornerstone of all privacy. If you don't have trust, you can't have privacy. And how we gain trust is through being transparent. So we update all our privacy policies to include what we're doing with de-identified and aggregate data. We also understand that not a lot of people read privacy policies. So one of the things we've done to help this is we've added privacy frequently asked questions on our website that are written in very plain and simple language that help everyone understand exactly what we are doing. And finally, we give users control. So we give users the ability to opt out of any of these large scale analyses without asking them for reasoning or justification. It's just a simple opt out if they choose to do so. With this being said, I'm going to take you through our architecture very briefly and talk through a bit of what we do specifically with the data. So all of this data is captured with probes within our network. I'm not going to go into detail about how that works, but once that data is landed on a server, it's pushed out to Google Cloud using NiFi. Once it lands there, it's put into a data flow job, and that data flow job removes all the opted out information. It sanitizes and de-identifies. It strips out all the personally identifiable information from the data. And then it does some analysis to retain secondary traits of that data. So this could be things like area codes or the country of origin of a device that are stored within that personal information, but are not the entirety of that data. Once all of this has been stripped down to the skeleton of the information, it's landed into BigQuery, where further analysis is done to remove things like duplicate devices, undesirable devices. These might be things like roaming devices from an IoT device that's not actually part of what we're looking to analyze. As well as we generate a system-based universal unique identifier. So this identifier is generated by the system as the only identifier associated to any of the information from this point forward, meaning there's no tie back to any of the personal information. Once this is done, our data is pushed through to an analysis layer. At this layer, we do a lot of different work to reduce the amount of data that we're storing. So this includes collapsing down each device into a timeline of what happened to that device as opposed to all the individual events. We also calculate an assumed home and work neighborhood. We'll talk a bit more about how that works and how we preserve privacy in that step on the next slide. We also then include a GeoID to each location, which is used to apply market share. And finally, we compute all of our API queries against this aggregated data set. So our final layer is our output layer, and this layer is built in App Engine, and it allows users to query and ask things like, what are the number of visitors in a given polygon at a given time? And they get a result returned back from the analysis layer. All of these results meet our privacy thresholds and are about large aggregate groups. We'll talk a bit more about how this is utilized in some real world cases in a couple slides. So the first thing I want to talk about is our assumed home and work neighborhood analysis. So the first thing we do is we look at what towers a device is connected to over a period of time. In this given example, we're going to look at a 1 week period. In this image, we can see two distinct clusterings of towers that this device were to connected to during the time. The first one being on the left here, and the second being on the right. The one on the left has a much higher total time spent, so we're going to look at that cluster specifically. And there's a lot of research that's showing the time most spent in a given area is likely that home, or the home is likely within that area. So taking this cluster, we're going to place a polygon around the initial tower with the highest weight. We then are going to shuffle that polygon across the different towers to try to find a closer representation of where the home area is. So we continue to shift this towards the higher weighted towers until we eventually hit that lowest weighted tower and get a rough estimate of where the home neighborhood would be. From here, we overlay that polygon onto a set of polygons that are based around Canadian Statistics Canada information of where neighborhoods are. So these are important neighborhoods that are used in statistical analysis of demographics and what we use for our market share. So by applying these neighborhoods, we use an ST-within function to determine exactly where that polygon is. And then we only store that blue polygon that is much larger as the home area for that device. So this again strips away us storing any of this information that's really detailed, and we go to this higher level piece of information to just understand the neighborhood, which is used in that further analysis. One of the big projects we've had come online since COVID-19 started is our Data for Good program. Within this program, we're providing governments as well as academic institutes access to our information at the aggregate and de-identified layer to help them solve problems related to COVID-19. This could be things ranging from how healthcare should be impacted and what should be done for healthcare institutes through to economic recovery as we're trying to reopen our economy. We're doing this under a strict set of rules, which are outlined on our Data for Good website. These include things like these cannot be used for police enforcement. The data cannot be used in any way outside of the typical usage we have outlined within our privacy policies. We will not reduce any of our privacy thresholds for COVID-19. We are staying strict to everything we've transparently given to our customers going forward. But this has been a very powerful offering that many of our provinces, federal government, and several cities are using as well to try to help in the fight against COVID within Canada. This is one specific example of how this data can be used. This is looking at social distancing, which was very important in the early stages of COVID-19. Really understanding where people are leaving the home. So in these maps, you'll see yellow as being more people than normal being out of their home. As we head towards that greenish blue that's in the middle of the scale at the bottom, that's typical behavior pre-COVID-19. As we get into the dark purples, that is less movement behavior. Now I want to zoom in on one specific area to show a good example of how this data can be used. So as we're zooming in here, this is the area surrounding Toronto, which is the capital of Ontario, which is the largest province within Canada. To the north of the map, you can see these areas lighting up in yellow. This is a very remote and rural set of communities that are very popular for cottage goers. And one of the things we immediately started finding in the data is that there's a large volume of people traveling to these areas from the big cities to try to get away from where crowds were. The concern here is it puts a real strain on hospitals in these areas that may only have 1 or 2 ventilators available at any given time. And if there were to be an outbreak in these communities, it would affect them much stronger than it would a larger city that has more ability to handle within their healthcare system. So this was being used to understand where to redistribute PPE in order to really help in fighting COVID. Another way of looking at this is the public health lens and trying to understand which communities are interconnected so that if an outbreak happens in one community, you know which other communities are likely going to be affected. So, by looking at large aggregates of how people travel from one city to another, we're able to start determining linkages and how closely linked different cities are. So, this is looking at 3 steps from Vancouver. So, this is taking Vancouver and then going up to 3 steps away and showing the interconnectedness of communities. This can be used, say, if there was an outbreak in Vancouver, how long would it take to spread to somewhere like Parksville that you see at the northwest side of the map? Or how long it would take to spread to Hope? What's the path of travel for that, and where would you see other outbreaks happening before you see it there? And this can be really critical in trying to figure out how to stop the spread of the disease. So there's a lot of numbers behind these maps, and BigQuery is what really makes this possible. So we have 74 billion records per month coming in. We have 275,000 unique points mapped out to over 5,000 unique polygons across the country. There's 522 days of data being used to analyze this. This includes things like building baselines from previous years, understanding the existing data today, and going far beyond that to try to predict what might happen in the future. And finally, there's 1.2 petabytes of data being analyzed. This is a massive, massive amount of data. And we're able to do this 25 times faster than we could with our previous Hadoop infrastructure. And that's really the power of Google Cloud here, is we're able to do this just because we have BigQuery GIS. We couldn't do this with our previous technology, and we wouldn't have been able to help in the fight against COVID-19 without having the access to this kind of technology. And again, today we're announcing our TELUS Insights API, which allows Canadian companies to get access to this type of information through a queryable API, where they can build out their own reports and analysis of what's happening across Canada. And to get more information on this, you can contact myself or the TELUS Insights team through our website, telus.com/insights. And back over to you, Chad.
So, Joe, thanks for joining me in the presentation. Thanks for announcing the launch of TELUS Insights in the presentation, and also thanks for the work you're doing. I mean, that's it's just a really great example of how we can bring these tools and this data together, to do good stuff for people, that need people that need to understand this, like public policy decision makers. So I really appreciate that. So to wrap up, everyone, by the way, this is the last slide. So if you're tired, we're just about there. So hang on. But to wrap up, I wanted to talk a little bit about the context that we are or have developed here at Google around geospatial analytics and how we're thinking about all the different areas of it. You can tell a little bit about this, that we foreshadowed it with the rest of the talk because we talked about imagery, we talked about tabular. So I just wanted to wrap that all up with one slide. On the left side, you see the types of data that frequently go into geospatial analyses, right? Tabular, imagery. On the bottom here, there are preformed data assets. The Earth Engine catalog, the Descartes Lab catalog, BigQuery's own public data catalog. There are a bunch of assets that we have just available for folks to start working on. In the center here, these are the capabilities that a wide-ranging geospatial analytics practitioner will need. They have to work on tabular data. They have to work on imagery. Maybe your use case doesn't use one of those, but we need to build it out for those who do. The bottom ones here, mapping and data visualization, right? You need to be able to get your results on a map, otherwise they're kind of meaningless. And we need to be able to bring to bear machine learning and artificial intelligence into this so that we can do predictive analyses as well. Once you bring all of those capabilities together over these data assets and types of data that are shown here on the left, then you get all of these use cases. So the ones that I described earlier, the ones like Joe described, and it really is our thesis here, and we're seeing this being borne out, which is really exciting, that once you have these capabilities available at the scale that they're available at inside of Google Cloud, you can do your analyses over much larger data sets and do much more interesting and ultimately impactful analyses for your users, for your customers, or for the public. So with that, thank you very much for spending a bit of time with us. My name is Chad Jennings.
And I'm Joe Bettridge. Thank you very much.